This is George Graybill, and I'd like to read to you from the book Stuff, or the Fortunes, Foibles, and Fiascos of Those Who Sought to Understand Matter. This will be chapter 12, called Deeper into the Atom, or How Can You Be in Two Places at Once When You Aren't Anywhere at All? The subtitle of the chapter is the title of the second album by the Fireside Theater. If you don't know what I'm talking about, ask your grandparents. Quantum mechanics is the branch of physics that deals with events at the atomic scale by treating matter and energy as coming in little packets called quanta and having fixed values. The work of Planck, Einstein, and Bohr, you heard about in chapter 11, was just the beginning, and is called the old quantum mechanics. The work that followed led to some very strange conclusions, such as two things can't be in the same place at the same time, but one thing can be in two places at once. You have now heard that waves can sometimes behave as a parade of particles. What is even stranger is that particles can behave as waves. This is observable for very small particles such as an electron. But do large particles have a wavelength? They do, but they are much too short to measure. Suppose you are running at a speed of 3 meters per second and that you have a mass of 60 kilograms. Your wavelength would be about 4 times 10 to the minus 36th meters. That is a billion trillion times smaller than the width of a proton. So don't worry about your wavelength. No one can see it. It was promised earlier that we would come back to the strange conclusion that light is both a wave and a particle. This mess is called the wave-particle duality. It appears that neither view can completely describe light. Both are properties of light, but they can't be observed at the same time. This is one of those cases where scientists give something that seems impossible a sciencey sounding name to make it seem logical. In this case, that name is the principle of complementarity. It sort of means both things are true, but not at the same time. Even with a great name like that, wave-particle duality has been a hard sell. It may be of some help to know that light usually acts like a wave when it's going somewhere and a particle when it gets there. Ready for more? So light can be a wave or a string of particles, and a particle can be a wave. In the 1920s, scientists tried treating an electron in the atom as a standing wave. It's called a standing wave because the electron isn't going anywhere away from the atom. Try plucking a tightly stretched rubber band. The fuzzy shape you see is a standing wave. It was starting to look like the energy levels of electrons in an atom each represented a standing wave, and that only waves of certain energies and shapes were possible. In 1925, Austrian physicist Edwin Rudolf Joseph Alexander Schrodinger put it all together with what is known as the Schrodinger equation. You've been working much too hard trying to grasp the strange ideas of modern physics. As in earlier chapters, we will take a break and hear about the strange personal life of a famous scientist. Edwin R. J. A. Schrodinger is a good example of a scientist with notable quirks. He was raised in a religious household, but turned out to be an atheist when he grew up. He studied philosophy and Eastern religions. From a branch of Indian Hinduism, he picked up the hypothesis that individual consciousness is not separate, but is part of a bigger universal consciousness. It sounds like his atheism had a kind of warm, fuzzy side. Edwin worked as a professor at universities all over the world, including the United States, Germany, England, Ireland, Scotland, and India. He didn't stay long at most of the schools. In some cases, it had to do with disapproval of his unusual living arrangement. For much of his life, he lived with two wives, his own and someone else's. Here is a picture of Irwin at home, relaxing with his wife at the top and the other woman on the right, and their dog. Back to physics. When the Schrodinger equation was applied to the one electron of a hydrogen atom, it predicted the allowed energy levels of the electron. These values agreed exactly with those of the Bohr model. Have you heard of electron clouds? Well, forget them. The Schrodinger equation predicts the probability of an electron in various positions around the nucleus. The result is often shown as something that looks like a cloud. What the picture is actually showing is the probability of the electron being in different locations. The darker parts of the so-called cloud are where the electron is most likely to be. A better name for these clouds is orbitals. The orbitals are described by four numbers called quantum numbers, which indicate four things: n, distance from the nucleus; L, the shape; m, the direction of orientation; and s, the spin. There is a rule called the Pauli exclusion principle that says two electrons in an atom can't have the same set of four quantum numbers. This is like saying that two things can't be in the same place at the same time. So far, this sounds logical, but wait. Here is a picture of the electron orbital of the ground state of hydrogen on the left, followed by two excited states. One odd result of the Schrodinger's equation is that we can calculate many important properties of an electron, but we can't know everything at once. For example, if we calculate the exact position of an electron, we can't tell how fast it is going. Likewise, if we know how fast it's going, we have no idea where it is. Trying to observe an electron doesn't help, because observing changes it. It's sort of like this. You can't tell what a 4-year-old is doing when he's alone in his room. As soon as you open the door to observe him, he will stop doing what he was up to, especially if it was something he wasn't supposed to be doing. This is called the Heisenberg uncertainty principle, after the German physicist Werner Heisenberg. Then there's the problem of quantum entanglement. Sometimes particles are stuck together in such a way that we can't measure the properties of either, only the sum of the properties. They are said to be superimposed, and their properties are entangled. Now we separate the particles at some distance and measure the property of one of the particles, say its spin. If we measure the spin of one of the particles, the other particle will immediately start spinning the other way. This happens in 0 time, even faster than the speed of light. People are still scratching their heads on this one. Einstein, for one, didn't like this at all, and thought there must be some explanation. He said he didn't like the idea of spooky action at a distance. It gets worse. Another result of quantum mechanics is that nothing can be in two places at once. Wait a minute, I got that wrong. I'm sorry. Is that something can be in two places at once. It sounds like a superpower. Just as properties are superimposed, the different paths of a particle can be superimposed. A particle can take two paths and end up at two different places at the same time. This is pretty well proven and extremely disturbing. Einstein didn't like this one either. He said the more successful quantum mechanics becomes, the sillier it looks. We are asked to believe that something can have two properties or locations at the same time, but only if we aren't watching. As soon as we make a measurement, the particle decides which it is. There are several interpretations of the illogical results of quantum mechanics. The most popular one still appears to be the one called the Copenhagen interpretation. This is a combination of ideas batted back and forth between Niels Bohr and Werner Heisenberg between about 1925 and 1927. These are some of the main points of this interpretation. 1. Quantum mechanics predicts only the probability of the value of a given measurement. 2. When a system is measured, it settles on one of the possible values. Before measurement, the values are superimposed. Some properties can't be measured exactly at the same time, such as speed and position, the uncertainty principle. A particle has both wave and particle properties, but not at the same time, the complementarity principle. Atomic scale processes can't be observed directly because observing them changes them. There are about a dozen other interpretations. The many worlds interpretation proposes that when one of the many results of a measurement is obtained, all the other possible results exist in alternate universes. Okay? The different interpretations correspond to different philosophical ideas about reality, time, and human consciousness. We will save this mind-boggling maze of ideas for later chapters. Schrodinger didn't like much of the Copenhagen interpretation. To point out what he thought were the ridiculous part, he proposed this thought experiment. Imagine that a cat is sealed in a steel box. Inside the box is a device that can release a deadly gas that will kill the cat. Whether or not the device is triggered depends on an atomic scale event in which a particle is in a superimposed state. One state releases a particle that triggers the device and that releases the gas, and the other state does not. According to the Copenhagen interpretation, the cat is both dead and alive until the box is opened. Einstein thought this was pretty funny and said that Irwin was one of the few quantum scientists who had a grip on reality. And that is the end of chapter 13. Chapter 12. The next chapter, chapter 13, is called A One-Electron Universe, subtitled An Electron Joke. If you look down, if you scroll down, you'll see a link to a place where you can buy the book, look at some of the book, read the reviews and so forth. And if you look in the bottom right-hand corner of the screen, I think that's where it is, you'll see a subscribe button where you can subscribe to my YouTube channel. So that's all for now. I'll see you next time. Bye.